Swayam Prabha. Digital India. Educated India.
So, we continue with our discussion on the module deadlocks, occurrence and mitigation. So, if you recall, in our previous lecture, we had basically discussed the nature of the deadlock, why deadlocks occur in a system, some of the necessary conditions for deadlock to occur and some of the data structures that are typically used, for example, the resource allocation graph, so that you can keep track of the processes and what are the resources that its process are currently holding. So, we continue with our discussion in this present lecture. This is the second lecture of the module. Here we start our discussion on some of the methods for handling deadlocks. Okay. So, we saw what a deadlock is, why deadlock occurs, but now let us see in a real system, if a deadlock occurs, what are broadly the approaches or measures that are taken to handle them. So, talking about the broad approaches, there are 4 broad approaches which also we mentioned earlier. First one is something called ostrich algorithm, which is basically a very simplified thing where we ignore that deadlocks has taken place, ignore the situation, and incidentally most of the operating systems that are used today, they use this approach. They do not spend any time and effort for detection of deadlocks, mainly because deadlock is a relatively very infrequent event and the overheads for handling deadlocks is too high. So, their approach is let deadlocks happen, ignore it, let the users detect and take some brute force measure to avoid or prevent the deadlock. Okay. Now, the other 3 approaches you can say are some approach where you detect whether deadlock has taken place in a system, based on that you try to recover from the deadlock. Okay. And third method is you try to avoid deadlocks, you ensure that deadlocks will not occur in a system, try to avoid them whenever there is a chance of a deadlock. And the last one is very rigid, you are preventing deadlock by some very strong measures, deadlocks will never happen. Okay. Let us see these approaches one by one and let us try to understand their advantages and disadvantages. Now, the first algorithm, as I said, ostrich algorithm, the name of this algorithm is borrowed from a story which I am not sure whether it is true or not. The ostriches, the birds, whenever they are attacked by predators, it is said that they hide their face in sand. They hide their face in sand and assume that nothing is wrong, everything is fine. So, the basic idea behind the algorithm is taken from that story. So, in this ostrich algorithm, what I said is that first thing is that, as I said, most of the modern day operating systems like Windows, Unix, Linux, they follow this approach. This is a very simplified approach, basically this is a no approach, it does not do anything. So, here the operating system pretends that there is no problem, deadlocks never happen in the system, even if deadlock happens I do not care, I will not do anything. Okay. So, basically the approach taken by the operating system is do not do anything special, do not do any kind of deadlock handling, let deadlocks happen, let deadlocks occur, let us try and recover from deadlock after the user detects that the deadlock has happened, but the operating system will not do anything. But as I mentioned, why is this approach used in the modern day operating system? So, why do not they handle deadlocks automatically? So, this is important to understand that why this approach is followed, because the first motivation is in reality the chance of a deadlock happening is very rare. So, if you spend too much money and effort on events that occur very rarely, then on the average the cost of your system can go up. So, what this approach says, because in reality deadlocks occur very rarely. Moreover, when you see the approaches for handling deadlocks, you will see that the cost of avoiding or preventing deadlocks is rather high. So, would you like to spend a high cost for something which happens very rarely? If you spend the time and effort, so every operation will become expensive for you. You will have to spend that means additional cost or overhead for any process you run, for any situation you are in. Okay. So, these are the 2 points that motivates the OS designers to follow this approach in many of the modern day operating systems. Okay. Fine. So, essentially we are making some kind of a trade off. Trade off is convenience. Convenience means we want to reduce our cost, because deadlock is a rare event. We do not want to incur any overhead because of that, but we are trading off convenience with correctness. In this context, correctness means a deadlock can happen and deadlock can disrupt the operation of the system. So, I am not doing anything for that. So, correctness in this context means somehow the system will avoid or prevent the occurrence of deadlock, but here we are not doing that. So, convenience we are giving more priority as compared to correctness. Okay. Now, there is another reason why modern day operating systems do not really take this deadlock thing very seriously, is that in modern day system, as you know, hardware has become very cheap. We have much more memory, we have bigger disk spaces and other things. So, typically resources which were very sparse in computer systems 20, 30 or 40 years ago, today resources have become very cheap and they are available in plenty. So, deadlock due to resource constraints or unavailability of resources has become a relatively rare phenomena. Okay. So, deadlock, because there are no resources, that chance is also very less. So, in this ostrich algorithm, the idea is that if at all deadlock occurs, how do you detect? So, as a user, you are running a program on a terminal, you find that somehow your program is hanging, your terminal is hanging, it is not proceeding any further. So, you can identify that something wrong has happened with your program, possibly deadlock, possibly something else. So, you will have to take the responsibility to take care of the situation. Operating system will not do anything for you. So, it is the responsibility of the user. Normally what we do, we use some kind of brute force technique, that either we kill a process. There are some commands in all operating system in which you can stop or kill a process forcibly, force quit or something like that, or in the worst case you can reboot the system. You can boot the system, restart it, and the computer system will again start operating normally. Okay. So, these are some of the brute force techniques which a user can adopt in such cases. Okay. Fine. Now, let us look at the second approach, where processes are requesting for resources, they are acquiring resources, but operating system is maintaining some information about all these things, and there is a mechanism by which automatically you can try to detect whether a deadlock has taken place or not, and if a deadlock has taken place, you try to recover from the deadlock. And here we are trying to look for an automated system where the user is not interacting, let the operating system do it in an automated way. Let us see the approach here. Some of this we have already discussed before when you had talked about the resource allocation graph. Approach is something similar. So, first let us talk about deadlock detection, how we can detect whether a deadlock has taken place in a system or not. Okay. Now, as I said, the operating system has information about the total number of resources available in the system, how many processes are running, and whenever a process is requesting for a resource, what are the resources that have been allocated to the process. So, all this information are available with the operating system. Okay. So, the OS maintains all this information. Basically, it maintains information about the processes holding resources, that what are the resources that are currently allocated to a process and what are the resources the processes are requesting for. The processes may be waiting for some resource, and we discussed earlier, one convenient data structure is a graphical representation, namely the resource allocation graph, where if you recall, there are two kinds of vertices. Circular vertices indicate the processes, rectangular vertices indicates the resource types, and edges, there are two types of edges from process to resource or resource to process, indicate that either a process is holding a resource or a process is requesting for a resource. Okay. So, here we discussed this earlier also, that whenever there is a simplified scenario that there is a single instance of each resource type. Every resource type has a single copy, there is one printer, there is one scanner and so on. So, if such a scenario is there, then it is very easy to detect whether a deadlock has taken place by analyzing the resource allocation graph RAG. Any directed cycle in the graph will indicate that there is a deadlock. So, the presence of a cycle in the graph, in fact, this is a directed cycle, a cycle with an edge, directed cycle. This will indicate that a deadlock has taken place, and all the processes that lie in that cycle can be identified as the processes which are involved in deadlock. Suppose I find P1, P3 and P5 are present in that cycle, which means that they are fighting for the resources and they have fallen in a deadlock situation. Now, the other issue is that this deadlock detection, that means checking this RAG, that whether there is a cycle or not, this is again some algorithm has to be run, some function has to be called. Now, the question is how frequently we should run this algorithm. Now, well, one thing you can say that this detection algorithm you can invoke every time a process requests for a resource. Every time a process requests for a new resource, you check that if I allocate this resource, can the processes fall in a deadlock. This is fine, but if you call this function too often, your overhead will also increase. You will have to run this algorithm many times. So, too frequent invocation of deadlock detection algorithm may result in relatively high overheads. So, we will have to strike a balance. Okay? You should not invoke this too frequently, you should invoke this whenever it is required. So, let us take a small example. Let us take a scenario where there are 7 processes running in the system A, B, C, D, E, F and G. Let us look at the resource allocation graph on the left. This is a resource allocation graph, and there are resources R, S, T, W, U, V, these are resources, and as I said, we assume that each resource has a single instance. So, you can see the edges. The edge from a resource to a process, for example, this edge indicates that the resource R is currently held by process A. But you look at this edge, for example, an edge from a process E to a resource V, it indicates that the process E has made a request for resource V. V may not be available now. So, the process is waiting for that resource. So, there are 2 kinds of resources, and as you can see, all the edges have a direction, either from a process to a resource or from a resource to a process. Now, this table on the left also tells you what are the resources the processes are currently holding. For example, A is holding R, this edge I showed, D is holding U, this edge, E is holding T, this edge, F is holding W, this edge, and G is holding V, this edge. And some processes are waiting for some resources which are shown in the last column. For example, D is waiting for two resources S and T. Look at D. D is waiting for this resource S as well as it is waiting for this resource T. Right. Now, given this resource allocation graph, this is your REG. You look into the REG and try to identify directed cycles in this graph. Now, if you run a graph algorithm to detect all the cycles, here you will find that there is a single cycle. This is the directed cycle in this graph. And on the right, we are only showing this particular cycle, which involves three processes D, E and G, and of course, three resources R, U and V. So, in general there can be more than one cycle also, but once you identify the cycle, you try to find out which are the processes which are involved in this circular wait or in this you can say deadlock scenario. So, once you have an idea which are the processes that are involved in this deadlock, now you know that how you can handle this deadlock, which processes you can remove or you can kill. Let us see. So, this is for a single instance. Now, let us look at the scenario where a resource can have multiple instances, like in the resource allocation graph we said a resource node can have multiple instances indicated by dots. So, a resource R1 can be having 3 instances. So, when you have this kind of multiple instances of a resource, presence of a directed cycle in the REG is not a necessary and sufficient condition that a deadlock is there. There may be a deadlock, there may not be a deadlock. The previous method that we discussed just now, it works only when there are single instances of its resource type, where each resource type has a single instance, then only this will work. But unfortunately, in practice this is very rarely true, because in general all resources have multiple copies. So, there can be multiple instances of every resource. So, if there are multiple instances, we have to dynamically check that whether resource requests that are being generated by the processes should be allocated or not. We shall be discussing some of these methods later in our next lecture. Now, basic idea is that in such a scenario where multiple instances of each resource type are there, we have to have a dynamic algorithm where we continuously keep track of the situation. We continuously check whenever a process is requesting for a resource is being allocated to a process, is there any chance of a deadlock happening? If we detect that some chance of deadlock is happening, we may ask the process to wait, that well, we cannot allocate the resource to you right now, you will have to wait. Okay. Now, at every instance when you are doing this check, we have to basically find out whether there is a scenario or there is a sequence of process execution where all the processes can finish. So, what I mean to say is that suppose there are 4 processes running in the system P1, P2, P3 and P4. So, each of them are holding some resource, each of them are requesting for additional resources. So, we check if there is some sequence of process executions through which all the processes can complete. For example, we may find that there is a sequence where P2 can finish first, then P3 can finish next, then possibly P1 can finish then, and finally P4 can finish. So, there is a sequence of process executions which exists through which all the 4 processes can finish their executions by acquiring all the resources they need. And if we can see that there is no such scenario, no such sequence like this exists at any particular point in time, then you can say there is a chance of a deadlock. So, the basic idea is that every time there is a request for a resource, we check that if the resource is allocated, can there be a chance of a deadlock? If there is a chance, we do not allocate the resource. So, this algorithm we shall be discussing later. This is called the Banker's algorithm. This we shall be discussing later. Okay. And the other question I discussed a couple of slides back, that how frequently should we invoke this deadlock detection algorithm. Now, this frequency of invocation depends on a number of factors. First, of course, most importantly, how frequently do we expect deadlocks to occur in our system? If we find that deadlocks are happening quite frequently, then you need to call it frequently. But if we find deadlocks are happening once in a day, then why invoke it every minute? Let us invoke it every 2 hours or every 1 hour. Okay? So, that is a kind of trade off you can make depending on the frequency of real occurrences of deadlock that happens in reality. Okay? And secondly, for recovering from deadlock, here the only method for recovering from deadlock is that some of the processes has to be rolled back or killed. Suppose I find that in a cycle, in the early example we saw that there are 3 processes involved in the cycle. So, any of the 3 processes we can kill, we can abort, we can roll back. So, whatever resources that process was holding will get released. The other processes can acquire those resources as required and they can complete, but we do not know whether we have to roll back 1 process or 2 processes. That we will have to find out by rolling back and checking this deadlock detection algorithm again and again. Okay. So, basically we have to roll back at least 1 process for every cycle in the REG, right. And if we invoke this algorithm frequently, possibly we will have to kill 1 process whenever there is a deadlock, there is a cycle. But if you call it infrequently, for example, after 2 hours we are calling it and we suddenly find that there are 3 cycles found in the REG. So, we may have to kill more than 1 processes. We have to identify all the processes, which may be difficult if there are multiple cycles in the graph. So, this is basically a trade off, that how frequently you need to invoke this deadlock detection algorithm. Okay. So, now the question is recovering from deadlock. Suppose we have invoked the algorithm, we have found out that the deadlock has taken place. So, what to do next? Recovery from deadlock. So, here again there are multiple options which may be possible, but of course, you cannot use all of them for all scenario. The first one is wherever possible you can use resource preemption. Suppose you find that there are 2 processes, let us say P1 and P2, which are involved in a deadlock. You take away the resources currently held by P1. Do not kill the process P1. If the resources are preemptible, take away temporarily, give it to P2 if P2 is waiting for them. And later on, when the resources are again available, give it back to P1 and P1 can resume. So, the idea is you take a resource away from some process, of course, which are involved in deadlock, but we are assuming that the resources are preemptible. That means, you can take away a resource from a process without killing it, without aborting it. So, this approach, although looking simple, but is not possible for non-preemptive resources. some resources have to be used by a process in a dedicated way. You cannot simply take it away. If you have to take it away, you will have to restart the process again from the beginning. You will have to kill the process, right. This is one approach. The other approach, of course, it incurs more overhead. This is something that is referred to as process rollback. So, what you do is that, suppose this is our axis of time, this is our axis of time. Periodically, we save the state of a process. These points are referred to as checkpoints. We do something called checkpointing. Periodically, we save the state of a process. That means, how far the process was executed, the state of the process control block, the resources it was holding, whatever relevant information, so that we can start the process again from that point. And if we find that the process has been involved in a deadlock at some point in time in the future, what you do? We roll back to processes to one of the latest checkpoints. For example, somewhere here we identify that the process is involved in deadlock. So, we roll back the process to the nearest checkpoint. The advantage is that, you see, some part of execution is already done. So, we need not have to redo that part of the computation. Only from the last checkpoint, whatever was done, that will have to be done again. Okay. So, this is the basic idea. Roll back a process to one of its saved checkpoints if it is found deadlock. But this kind of checkpointing may be a little problem if the process influences other processes in various ways, which are sometimes called side effects. Because if there are a lot of cooperating processes, a process is sending messages, they are interacting with other processes, then if you roll back one process, it may need other processes also to get rolled back. So, this process is not independent, you cannot independently roll it back. The similar cascading effect will happen for the other processes as well. Okay? These are called side effects. Fine. And the third approach is that simply terminate a process. This is the easiest approach to do. This is the brute force approach and also the simplest. See, every operating system has a way to kill a process. For example, in Unix or Linux, there is a command called kill. You give kill -9, then the process ID. So, this will kill the process with that particular PID. So, from a terminal, if you give this command, that process will get killed. Now, the question is that which are the processes that need to be killed? See, this can be done by the user, this can also be done by the operating system. So, as I said, the OS is analyzing the REG, resource analysis graph, resource allocation graph, and it will be trying to kill some of the processes that are involved in deadlock. Now, if we kill a process, suppose that process was holding 3 resources, all those 3 resources will get released. So, other processes can take them. Now, there are 2 options. One option is you kill all the processes which are involved in deadlock, but that may be too strict a measure, you need not have to kill all the processes possibly. Option 2 may be better, you kill the processes one at a time until you see that the deadlock has been eliminated, right. So, if you have a choice, if there are 3 processes you have to decide which one to kill, you find out how much execution these processes have already gone through. The process which has consumed lot of CPU time, better not to kill it, because if you restart it later, it will again have to run for so much time. So, try to select a process that has not run too far. That may be a better process to select, because the cost of restarting will be less. right. So, these are some of the broad approaches using which you can handle deadlock once you detect that deadlock has occurred in a system. Okay. Now, the third approach is called deadlock avoidance. Now, in this lecture we shall be discussing some of the basic concept behind deadlock avoidance. In the next lecture we shall be discussing a detailed algorithm for that. Now, let us try to understand the basic philosophy for why are you calling it avoidance. Like you see, you are moving in a road, let us say you are moving along in a road, and in some points in time you see that there is a junction, you can move either in this direction or in this direction. You take a decision whether to move here or whether to move there. Suppose at every time whenever you make a decision, you see that well, this region is a little unsafe, there is a forest. So, it is safer to follow this path, the other path. The concept is something like that. At every point in time where you have to take a decision, you check that which decision will be safe for me. See, unsafe does not mean that it is a deadlock scenario. Unsafe means there can be a deadlock, but if you are always on the safe path, you can avoid deadlock altogether. The idea is that you always try to move from one safe state to another, never go into an unsafe state. If you can ensure this, that you are never going into an unsafe state, it means that you are avoiding the deadlock scenario from happening. Okay? So, we shall be discussing an algorithm later in our next class, which is called the Banker's algorithm. This is one of the most common algorithms that is used for deadlock avoidance. Now, first thing is that this is a general algorithm for deadlock avoidance. General means we are assuming that there can be multiple instances of each resource type. Each resource can have multiple instances, and this algorithm assumes one thing which may not be practical in all scenario, which is before a process starts execution, the process will declare its maximum resource usage. For example, the process will tell that I need resource R1 3 copies, resource R2 1 copy, resource R3 2 copies. So, it will have to declare beforehand. So, you see, now the thing is that whenever you are writing a program, you have to also specify how many resources you require. See, this used to happen in the early days of computing, where you had those multi-programming operating systems. There, whenever a job was submitted to a computer system for execution, as part of a job, the resource requirements are also specified. But in modern day systems, direct application of Banker's algorithm may be difficult, because a priori you do not know what is the maximum resource usage. During execution only you will come to know, right. And the other thing is that as part of this algorithm, the first thing I have already mentioned, that every process will declare that how much maximum resource it needs. Secondly, during execution a process may require a resource. So, what it will do? A process will be requesting for a resource. So, this will be like a system call. A process is making a system call, control will go to the operating system, and operating system will try to allocate or grant the resource to it. Now, I told about safe and unsafe states. Now, there is a decision the operating system has to take. Should I grant the resource or should I ask the process to wait? The idea is like this. The operating system will take a decision like this. It will check that if I allocate the resource, whether it can lead to an unsafe state. Can the state become unsafe? if there is a possibility of the state becoming unsafe, then it does not grant that resource to that process. It will say the process, ask the process, please come to the waiting state, you wait, let the resources become available, then you can resume your execution. So, the process has to wait. But if the state is not unsafe, if it is safe, then resource can be allocated and the process can continue. So, essentially in this algorithm, we have the concept of these safe and unsafe states. Okay. And another assumption is also there, which is central to this algorithm. It is this last point. It says that suppose a process has requested for a resource, the resource has been allocated to it by the operating system. Now, it is assumed that the process will not hold the resource for indefinite amount of time. It will use the resource, return it back to the operating system within a finite amount of time. This is another assumption we are making. Because if it holds it for indefinite amount of time, then it is a problem, this algorithm may not work correctly. It is assumed when a resource is allocated, finally, if the process gets all its resources, it will finish execution, it will return the resource back. Okay? Fine. Now, talking about the safe and unsafe states, see on the left we are showing some kind of a Venn diagram, which we normally use in set theory. Set of all states which are indicated by this outer rectangle is divided into two parts, the green part which are the safe states and this pink part which are the unsafe states. Now, as I had said, safe state means there is no chance of any deadlock. So, if you are in a safe state, there is no difficulty for you. You can proceed without any problem. But unsafe state does not mean that there is a deadlock. Unsafe state means there is a possibility of a deadlock. So, out of all the unsafe states, one small subset of those unsafe states may be the deadlock states. So, unsafe does not mean deadlock, but anyway, in the deadlock avoidance strategy, I avoid going into the unsafe state at all. Although unsafe state may not mean that there is a deadlock, but still I will remain in the safe state only. I will never go to the unsafe state. I will never cross this boundary. That is the idea. So, avoidance means ensure that the system always remain in the safe state, never allow it to move it to an unsafe state. This is the central idea behind this Banker's algorithm. Now, you try to understand one thing here. Here, number one thing I said that a process has to declare all its resource requirements in the beginning. Okay? So, the operating system knows what is the maximum requirements of a process. The OS also knows how many processes and how many instances of each process types are available in the system. So, having the whole information in a central place, the OS can take a decision that at any particular state of the system, is the system safe? So, when I call a system safe, I mentioned earlier already that if there is a sequence of process execution that is possible, by virtue of which all the processes can finish their execution. If all the processes can finish their execution, we say that the state is safe. So, every time a process has a new resource request, what the OS do? OS assumes that, well, suppose I allocate this resource to the process, will the state become safe? It will try to find out whether such a sequence of process execution exists. If it exists, it will say that yes, it is safe, I can allocate the resource. but if it is not safe, it will not allocate, it will ask the process to wait. Okay? This is the basic idea. So, this is actually what I just now mentioned, how to determine whether a state is safe. So, suppose there are n number of processes in the system P 1, P 2 to P n. So, a state is said to be safe if there is a particular sequence of processes. Sequence means an ordered sequence, P 1 followed by P 2 followed by P 3 at the end P n, such that all the processes can finish execution in the order that is specified in the sequence. Now, here one thing is assumed, suppose this process P 1 is executing first, let us say in the sequence. Now, P 1 may be holding some resources, let us say some resources. So, after P 1 finishes and when you start with P 2, so all these resources which P 1 was holding, these will be released. So, P 2, P 3, P 4 they may be using these resources if required. Okay. So, that is mentioned in the second point. For each process P I, the resources that P I can still request can be satisfied by the currently available resources in all the previous processes. Like say you have P 1, P 2, P 3 in this sequence you have to execute. Let us say we talk about P 3. P 3 is requiring some more resources, and that some more resources must be available either with P 1 or with P 2 combined, because after P 1 is finished it will release the resources, after P 2 is finished it will release the resources, and those released resources should be sufficient for P 3 to finish. That is what is mentioned here. So, whatever request P 1 has made can be satisfied by whatever is available in the system currently, plus all the resources that are released by the previous processes in the sequence for all j less than I. Okay. This is the idea for checking whether a state is safe or not. Now, this is what I said, that when a process finishes its execution, it returns all the resources it was holding. This is also the assumption, right. Now, let us take a small example and let us work it out. So, we are taking an example where there are three processes, let us say A, B and C. So, in this slide I am showing, in fact I am showing many different examples together. Let us see the first one on the top left. Let us assume there is a single resource type for simplicity. Assume that there are 3 instances which are currently free, and A has so many resources and the maximum resource requirement is this. So, you see that with 3 free resources, well, A cannot finish, A needs 6 more, C needs 5 more, but B needs 2 more. So, B can finish. So, it is possible for B to finish. So, after B finishing, these 2 resources it was holding will be released. So, free will be 3 plus 2, 5. With this 5 available resources, C can now finish, C needs 5. So, these 2 will also be released, 7. Now, A needs 6 more, so A can also finish. So, I can say that this state is safe. So, I have a sequence which is B followed by C followed by A. In this way, for every scenario you can check whether a state is safe or not. Let us check the second one. Here assume that there is one resource which is free. In fact, this is the second state actually. From here what is happening after B has finished, after B is getting its 2 resources. So, B will be having 4 and free was 3, now free will be 1. So, now B has got all its resources, B can finish. So, after B has finished, B has done. So, B is no more in the picture. Now, total free, this 4 will be released, now free is 5. Now, as I said, now C can finish. So, C had got all 7, C can finish. So, free is 0 currently. So, after C has finished, the free will be 7. So, now A can finish. Right. Now, here let us see a scenario here, the second one. Suppose same example. So, this was the initial state. So, there were 3 free resources. Let us suppose the process A requests for 2 resources, because all the remaining resources may not be requested at the same time. So, A requests for 2 resources, A requests for 1 resource, let us say 1. So, A had 3, after allocating the resources A will get 4. So, free was 3, free will be 1 less. Now, this 2, let us say 2 can be given to B. Let us say now B requests 2, B will be given, B will get 4, B will finish, B has all the 4. So, after finishing, these 4 resources will become free. Now, you see in the present scenario, A requires 5 more, C requires also 5 more, but the number of free resources is 4. None of A and C can proceed. So, you cannot find a safe sequence, this state is unsafe. See, this state is unsafe means what? It does not mean that this state that we are showing is a deadlock state. It is saying that if we follow a sequence B followed by C followed by A, then all the 3 processes can finish. But if A requests for 2 resources in the beginning, then after that you cannot proceed any further. You can only go to B, but A cannot finish, C cannot also finish, as can be seen from this last table. So, this is what we are trying to say is that safe and unsafe checking is important, because unsafe does not mean deadlock. Unsafe may mean that if the resources are requested in any arbitrary order, there can be deadlock, but if it is in some other order, there may not be any deadlock. So, here for the same example, I have showed 2 different sequences of requests coming. For one case the processes got executed fine, for the other case there was a deadlock scenario. Now, you see, we discussed the essential idea behind the Banker's algorithm, but we did not discuss the details, how it works. Now, in the next lecture, we shall be talking about the details of the Banker's algorithm, that as I said is the most important and common algorithm used for deadlock avoidance, and after that we shall be looking at deadlock prevention, that is the 4th broad approach. So, these we shall be discussing in our next lecture. So, we shall be discussing firstly the Banker's algorithm in detail, we shall discuss some examples, and lastly we shall look into deadlock avoidance algorithm, deadlock prevention algorithm, where deadlocks can never happen in the system. But we will see that the method is very restrictive, we have to put in lot of restrictions, lot of overheads to make that happen. So, with this we come to the end of this lecture. Thank you.